continue on from extending what we did last time. Last time we were talking about octahedral complexes, and we were looking at the d-orbitals. And let's think about this. One of those d-orbitals was the x squared minus y squared. They go along the x-axis and the y-axis. And so if we had hydrogens at the end of those axes, the hydrogens have 1s orbitals. And so one way we could write out the designation of these orbitals, and this is going to be throughout the notes today, so I wanted to just give you insight into how we write these things. We've got this d x squared minus y squared. And so we're just sort of, that's the orbital as it's shown. And if we say then this orbital here and here have the same shading, and this orbital here and here have the same shading as that one, we would say that those are in phase, right? And so we would say that this orbital, this designation for the d orbital, okay, has a positive sign in front of it. And if we want to say that this orbital is in phase with all of the hydrogens around it, we would say plus 2 of these hydrogen 1s's, and then plus these 2 hydrogen 1s's. So we have plus, plus, and plus, which just means they're all in phase with each other as they're appropriately in phase. Okay, so we have the non-shaded ones in phase with the non-shaded hydrogens, and the shaded ones in phase with the shaded hydrogens. And so this would be a low energy orbital because they're all in phase. Now what we could do to make an antibonding orbital is we could change these signs here, minus 2, 1s, and minus 2, 1s. So we would have shading here and a node, shading here and a node, no shading there and a node, no shading there and a node. Just by changing those signs. Everybody kind of see what we're doing with these? This is a shorthand because, I mean, how do you write out all of the, wave function for all of this? It wouldn't fit on the board. There's no way it would fit on the board. And so we've got to find some way to make a shorthand for when these things are interacting with each other in a positive way, meaning there's no nodes, or in a negative way where there's nodes that break the bonds. And so if there's a node that breaks the bond, then it weakens that bond. If there's electron density that goes between the two atoms, when there's no node there, then that strengthens the bond. Because if you think about what holds these atoms together, it's the electron cloud. And so if that electron cloud is all one shape and one shading between two atom centers, those atom centers have electron density between them, and they're going to be held together. Okay. But if there's a node, there's sort of a break in that electron density between the two atoms, and they can get further apart. Okay. So that's a little bit of deep background, sort of connecting what we did last time to the notes that we're going to have today. Now, all the pictures in the notes today are going to be going by way too fast for you to draw them, but that's because you have them on Blackboard, so you can download, and you'll have this video as well, so you can go back and look and compare the pictures with the little designations that we have. Now, the thing that you'll have to do when I'm going to test you on or do for the homework is if you know the symmetries of these things, can you determine the selection rules? And so we have several examples of that, determining the selection rules for spectroscopic transitions. I may ask you to interpret a few of these pictures, but in terms of drawing the pictures, probably not going to ask you to draw the pictures. I might put that on that last one on the creative section. So if you do like to draw the pictures and you think you're good at it, you'll have a chance to do that on the test, but that'll be on that creative part of the test. Can you draw a d x squared minus y squared in a bonding arrangement with 4 hydrogen 1s's, and you might be able to come up with this picture. So you'll get a chance to do that, but in terms of the requirements, I'm going to require you to be able to do the selection rules and the symmetries. Okay. So what we talked about crystal fields. We put an atom in a particular arrangement of other atoms or other molecules around it. And the symmetry of the arrangement gives us what we call a crystal field. We can describe that by a point group. And so we have, in this set of notes, 2 cases. We have the octahedral point group and the tetrahedral point group. We're going to go in great detail on both, but we're going to see more about the octahedral point group. The tetrahedral one is somewhat confusing. Okay, the octahedral I think is a little more easy to understand. So let's look at this. This is our chromium, and we've put 6 hydrogens around it. Let me just check the video and make sure we're capturing it. Yes. Okay. And so in Gaussian, we can run this chromium hexahydride, if you will, put 6 hydrogens around it, and we can have Gaussian generate all the molecular orbitals. So these pictures are the combinations of the different orbitals that that chromium has, along with the 1s orbitals on the hydrogens. And the nice thing about Gaussian is it gives us all of these energies over here on the right. And the ones that have little 2 electrons in them, those are occupied orbitals. And the ones that have been calculated that don't have electrons in them, those are the unoccupied orbitals. The ones that are unoccupied, there's the lowest one there, and that'd be the LUMO, the lowest unoccupied molecular orbital. And of all the occupied ones, there's a highest one that's occupied, and that's the HOMO, the highest occupied molecular orbital. And the difference between those two is the band gap. And the band gap is a critical thing to know if you're going to talk about a conductor or an insulator. A conductor has a band gap of 0. An insulator has a pretty large band gap. A semiconductor has a moderate band gap. One that can be excited thermally. So you warm up a semiconductor or put it in a slightly positive charge or negative charge depending upon the junction, and you can get electrons to hop up into the conduction band, and then they can conduct. So that's how our light emitting diodes work. That's how our memory chips work. We have a lot riding on this band gap in material science. So these are all of the little orbital designations, like this, what I've drawn on the board, for all of these orbitals here. So you can see it's pretty confusing, but some of these down here in the core are pretty understandable. We have the chromium core electrons, which would be the electron configuration that we just learned in the last set of this course. So we went through 1s, 2s, 2p, 3s, 3p, and so on. If you look where chromium is, okay, it's right here in the D block. Okay, so we have the 1s, the 2s, the 3s, 3p, the 4s, and then we have the 3ds. And so everything up to argon is going to be in the core electrons, and those don't participate in bonding. Now that's a claim. We're going to see that revealed here with this Gaussian calculation. We're going to go from the 1s all the way up to the valence band where all the bonding's happening. So let's go through all of the orbitals in this molecule. So starting down at the very bottom. So I've plotted all of those orbitals in this plot. This is the full molecular orbital diagram for chromium hexahydride. And look on the energy scale. This is kilojoules per mole. Those electrons in the 1s are really low, 600,000 kilojoules per mole down here at the bottom. And then we're going to zoom in up here at the top. So we're going to take this whole top region. So we see that the 1s orbital is way down there. It's very close to the nucleus, very low in energy. It's not going to participate in bonding. Okay, so it's filled with 2 electrons, and those 2 electrons are essentially on the chromium. So zooming into that region that I show with the bracket, this is the blue box. So now we see some more atomic orbitals. So we've expanded that y-axis, kind of zoomed in, and look what we see down here at the bottom. We see the 2p shell. So the n equals 2 shell for chromium is down here. And you see the 2s and the 3 2p orbitals. Just like you would expect for that Aufbau filling scheme, the 2s by itself and then the 3 2p's are triply degenerate. We have 2 electrons in all of those orbitals. But still so low, down at like 60,000 kilojoules per mole, we don't have any interaction with bonding. So these electrons in these orbitals really have no idea that there's hydrogens out there. They're not participating in bonding. So let's zoom in again. Let's take this bracket region and then expand it. So here we have now, we've zoomed in. We're starting to see the bonding area up at the top, but we still have that n equals 3 shell. So we have the 3s and the 3p's. Again, that brings us up to argon. Those are not the valence electrons for chromium. So they're not participating in bonding. So they're still core electrons. They're still not knowing that there's anything happening outside where the hydrogens are. And then we zoom in on this red region. That's the bonding region. That's the valence region. That's where the electron cloud is holding these atoms together. And this is where things get confusing. This is where you start to see splitting of the d orbitals and so on. So looking at this is the molecular orbital diagram. We still have some things that are recognizable. Down here at the bottom, we have a 4s and some 4p's, but notice we have some 1s's too. And so those are the bonding interactions with the hydrogens. Here we have some 4p's minus the two 1s's, and so those are the antibonding arrangements. And here's an antibonding for the 4s. And then we have the 3d orbitals thrown in here. We have the x squared minus y squared and the 2z squared, etc. there, and we have those down here as well. So we have some bonding, we have some antibonding, we have some interactions. Now when we get into MO theory, which is the next set of notes, we'll go into how we build up these orbitals, but I'm just showing you with this octahedral crystal field what we have for the chromium atom. Now this is a pretty detailed set of notes, and so that's why this is when the video really becomes important, because I'd like for you to go through this so that you understand how these orbitals work together. And in particular, you want to come back to this video after we do the MO theory and the projection operator, and then you can come back and see how these pictures were made. Now, this is a third-party endorsement of this set of notes and these videos. I got this email from a fellow in Germany, and he says, I'm an international master's student at Ludwig Maximilian University in Munich, Germany. And he said, just for information, it's me who was asking you questions on the YouTube lecture. So he was going through these and putting comments and asking questions. He said he's fascinated by the lectures, and this is the cool part. He says, I've taken a few online courses on spectroscopy from MIT and UC Irvine, but I'm happy to say that your lectures have provided me with a better imagination, information, and satisfaction than the other online course. So that's pretty cool. The neat thing about this is using these Gaussian pictures to explain MO theory and bonding, I've not seen that anywhere. It's certainly not in the book. I'm going way deeper than the book in this area of molecular orbital theory. And it is something that, you know, people are writing me about and saying, I didn't think about the electron cloud oscillating like you talk about. Most people just see those pictures and they have no idea what a p orbital really is. And so I'm giving you insight that it, like he said, it gives me a better imagination. Your imagination is how you solve these problems. And your insight into how the electron cloud oscillates is key to understanding bonding. And if you can understand bonding, you are going to be a good chemist. There's no way around it. So let's look at bonding. We've got this down at this 1s, so we've zoomed back out. We've got the 1s, and so I've drawn the picture of the 1s orbital, and it's so tightly bound, it's actually inside this little sphere that we draw for the chromium atom. Okay, so you can't see it. It's so tiny. It's so close to the nucleus. Okay, so let's go to the 2s. So here's the 2s, and now we can actually see the red shading. Of course, sometime later it'll be green because it's oscillating in and out as a sphere. It's got one node because it's a 2s. That node is a radial node, so it's inside that red region. So inside that red region, there'll be a non-shaded region and then a tiny little green region that's very close to the nucleus. And then here are the 2p's, 2px, y, and z. And you can kind of see them barely peeking out of the blue sphere that we use for the chromium atom. And we also have the Millikan symmetries for these. We have A1G for the sphere. How do we know what the symmetry of the s orbitals are? Well, they're top row. And so this is an octahedral crystal field. So you go to the top row, and that's A1G. Then the Px, Py, and Pz, you go find those in that octahedral character table, and it's T1U. So that would be the symmetry for all of the p orbitals, no matter what shell they're in. Anything with x, y, or z symmetry is going to be T1U in an octahedral field. So let's zoom in a little more and go to the 3s and 3p's. Now the 3s has two internal radial nodes, so it's going to be sort of red on the outside, and then there'll be a non-shaded, and then a green, and then a non-shaded, and then red really close to the nucleus. So it's kind of like an onion. It's built out 3 layers for the 3s. And then the 3p's, look, now they're getting larger. Look how much further they are from the nucleus. And now they're starting to potentially interact with those hydrogens. But we still have the the d orbitals and the 4s orbitals to interact with the hydrogens. So, and then same symmetries again for the s orbitals and the p orbitals. So notice you don't just use the symmetry one time. Anything with an x symmetry is T1U. Anything with a y symmetry is T1U. So now we get into the valence region or the bonding region. We have all of this mess, and we can see the electrons down here. This is the HOMO-LUMO gap. So we could look at the energies here, we could do a subtraction, and we could figure out what that HOMO-LUMO gap is. Taking that difference, so remember the Grotrian diagram problem that no one tried. If we take that difference, this is an energy level diagram. It's not a Grotrian diagram, that's reserved for atomic spectroscopy. But this is an energy level diagram. So all you have to do is take the difference between an occupied and an unoccupied orbital. And if it's allowed by symmetry, that makes it possible for a peak to be in the spectrum. Take that energy difference and convert it to wavelength. And that's the location of that peak in the spectrum. And then if you wanted to know the intensity, you'd actually have to calculate the transition dipole moment integral. But the symmetry rules will tell you if there's a peak there. And so if it's non-zero, you can just draw a line and put a peak on it. But how do you know where the wavelength is? You take the difference in the energy level diagram and convert it to wave numbers, or convert it to a wavelength. So let's look at some of these pictures. So this one down here, it's hard for you to see maybe from this distance, but this right here says 4s plus 6 1s. So it's a 4s orbital plus 6 1s orbitals on the hydrogens. And that plus sign means they're in phase, and so everything's red. So that 4s on the chromium is expanding, and the hydrogens are expanding. And so the electron cloud is just going and enveloping those hydrogens. At some time later, it shrinks and the hydrogens shrink. So those electrons are just pulsing, breathing in and out. And they are spending most of their time between those nuclei and holding them all together. These are the two d orbitals that interact with the hydrogens. And notice this one here, we have the x-axis and the y-axis. And notice they're different color. So the x is the same on plus or minus x, so that's x squared. The y is the same, plus or minus, so that's y squared. And they're different color from each other, so it's x squared minus y squared. So that's this one. That's the 3D x squared minus y squared, and I put a plus 4s on it to show it that it's in phase with all 4 hydrogens. On the board, I wrote them in 2 groups here, but really we just lump those together since they're the same sign. So plus 4s is the designation for that orbital. It's a shorthand. And then over here, this one is the z squared, and it's huge, so it's 2dz squared minus x squared minus y squared. So the x squared and y squared are the same color because they both have the same sign, minus and minus. This minus is up here. And then I have it plus 2 1s. Let's see. Really, probably should be plus 6. So that might be a little mistake there. Because there's 6 1s orbitals that are in phase with that orbital. Okay. So there were a whole lot of little things to type on these slides. So plus 6 1s. So all 6 of those hydrogens are in phase with that dz squared minus x squared minus y squared orbital. And so they're all in phase and all bonding. Yes?
The hydrogens don't have to be in phase with each other, they just have to be in phase
with the d orbital, yeah. So that's a good one. There may be other ways to write these little shorthands. And so you might, if you were trying to take into account the 4 hydrogens that were in phase with each other minus the 2 that are not, you might have a plus 4 and a minus 2. But in trying to determine what the best way or most concise way to write this little notation, I decided to keep it a plus sign if it was in phase with the d orbital. So yeah, there may be other ways to write the notation, but I think this makes sense. If we look at the plus signs on the hydrogens, that means they're in phase. So let's look at the antibonding ones, and this will clear things up. So here, we still do the bonding ones. Okay. So let's look here. We have a 4p we don't really designate X, Y, or Z, but this one happens to be the Z. You see that it's up and down. So that's the Z axis. So that would be the 4pz plus 2, 1s. Which one is this? We've been talking about the X, Y, and Z. What do you think this one is?
X.
Yeah, the 4px plus 2, 1s. So it's in phase with 2 hydrogens. And then this is the 4py plus 2, 1s. So those are all of the bonding interactions up in the valence band. The core electrons are too low in energy to really interact in this region. Okay. So we have the 4s interacting. We have the 3D interacting. We have some 4p's interacting. Okay, now let's look at what happened. Okay, so I think we're just looking at the splitting of the 3D atomic orbitals. So think about the 3Ds, right? If we're talking about 4p's interacting with yes?
I was wondering, so if we are dealing with chromium, why are there 4p?
Great, that's where I was headed right now. Yeah. So the 3Ds should show up before the 4p's, right? If you just have an atom of chromium. And those 3D orbitals are not split. There's 5 equal orbitals. And so look where they would show up. They would show up right after the 4s. You would have the 3D orbitals here. And then you'd have the 4p orbitals on the atom in space with no interactions with any other species. But because we put hydrogens on all the faces of a cube, then those d orbitals are either pointing at a hydrogen or pointing between the hydrogens. The ones that are pointing at the hydrogens can accept electrons and interact with those hydrogen 1s orbitals. And so think about this. Even though this is a really complex molecule, think about this with the particle in a box thinking. I've got a 3D orbital, let's say maybe this big, and I put hydrogens on the outside of that, and they're in phase, so now that electron cloud can go out past the hydrogens. What's happened to the box that electron is in? It's gotten bigger. So what happens to the energy? It goes down. So if the box gets bigger, the energy goes down. If the curvature goes up, if I have lots of nodes, the energy goes up. So an antibonding, even though the box is bigger for an antibonding orbital, I've got 2 nodes. And so that drives the energy up. So you can, even though these are really complex pictures, you can think about it using that particle in a box that you know so well because we've used it so much in the first half of the course. Think about the 3 things that you know from the particle in a box. If the box gets bigger, the energy goes down. So how it responds to size. Mass. We're really only dealing with electrons. But yeah, if the mass got bigger, the energy would go down because the mass is in the denominator. And then the quantum number goes from like 1 node, 2 nodes, 3 nodes. So if the quantum number goes up, the energy goes up. Quantum number tells you also how much curvature you have. And so if you've got lots of nodes, the energy's gone up. So those are the things that you learned in the particle in a box that you can apply to these really big and cumbersome pictures. So what's happened to those p orbitals is that 3 of the d orbitals went above the p orbitals. And so since those three orbitals went higher than the p orbitals, when we're throwing electrons in this molecule, now those electrons are going into the p shell instead of those d orbitals. So that's what we're looking at here, the splitting of the 3D atomic orbitals. So we've looked at these 2 down here, and then we have these 3 up here, the dxy, dxz, and dyz. So those have been pushed above the p orbitals. And so when you put electrons in from low to high, the electrons go into those p orbitals and not into these d orbitals. And so here's if you can look at this is the x-axis here, this is the y-axis there, and this is the z-axis going up. And so which orbital is this? It's got that plus, minus pattern. And what plane is that in? This sort of test to see if you can look at that picture and see what plane that orbital is in. There's three choices because there's three planes. There's the XZ, YZ, and XY. That's the XZ plane. Okay. So if I'm staring at the XZ plane, I might draw it for you real quick. So that we see the lobes of that orbital in the XZ plane, and I have the shading changing like this. And this is squeezing out this way and squeezing out that way. And that's what's happening in that orbital. So it's squishing out this way while those shrink, and then squishing out that way while these shrink. And notice that that kinetic energy, that movement of the electron cloud, is not aimed at any of the hydrogens. We have hydrogens here, 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 and here. And so there's been no interaction really to lengthen that box at all. In fact, it's kind of not in phase with these hydrogens, so it's kind of maybe even pinched a little bit, which is what causes the energy to go up. Yeah?
You said last lecture that if it's like the plus minus, that means they're multiplied together. But what is the so it's x squared minus y squared? Isn't that plus minus?
Yeah, and so those are on the axis, and so that's and there's the square. So the x squared has made both the positive and negative x positive. Yeah, so that's the x squared part. Okay. And then to make it a different color than the y squared, that you have used the negative sign. But that's a good question because you see the four color change, but they're not between the axes. And so this pattern shows up between the axes, and that tells you that it's a D, like this one would be the D x z. So x times z. And so that's actually that recognizing that those patterns are very similar will help you see when this is, which one is this, first of all? X times y. Yeah, so x times y. And notice it looks very similar to this one, the x squared minus y squared. And there are point groups where those two stay together. Okay, so the crystal field will split these in different ways. We have 5 d orbitals, and that's really one of the main reasons of going through this, is to see when they split and what goes with what. There's 5 orbitals, and in the octahedral and tetrahedral case, they go 2 and 3. So the ones that have lobes that go along the axes stay together. And the ones that have lobes that go between the axes stay together. There's 3 of those, so we always have a 3 and 2 splitting. There might be 2 on top and 3 on bottom, or vice versa. Okay, and so depending upon a tetrahedral or octahedral field, or whether you have a lot of electrons in the D shell or few electrons in the D shell, you will split this 3 and 2 or 2 and 3, and it'll always be these ones that either go along the axis or go between the axis. That's what's going to set up this splitting. And we saw that at like the second slide in this. It was the octahedral and tetrahedral, this 3 and 2 splitting. And you're going to get into that in advanced inorganic, because that's inorganic chemistry. It's with metals, and you're going to deal with the d orbital splitting. And so this lecture will be really important when you go into advanced inorganic. Go dig through YouTube and find this lecture. Go through it again so that you're refreshed on how the splitting occurs. Now we can do antibonding orbitals. So let's look at this one. So this is the bonding orbital down here in the bottom right. That's that dz squared minus x squared minus y squared in phase with 6 hydrogen atoms. And what if it's out of phase with those 6 hydrogen atoms? You see up here, you've got some color changes. It'll be a little difficult to see, but that the hydrogens being out of phase has really shrunk that d orbital. It's crammed down into this tiny little space. So inside that little square that I've drawn is the dz squared minus x squared minus y squared. And those hydrogens have really squished it. So 2 things have happened. That d orbital has got a smaller box, and it's way more curvy, because if you cram that wave into a smaller space, then it has to go up and down quite often before it goes out into space and goes to 0. So So very high curvature to that wave function, which means it's high in energy. Does everybody understand the curvature energy thing? That's the Schrodinger equation. It's the second derivative of that wave, and the second derivative is curvature. And how do I see curvature on these? How small are the lobes, and how many nodes does it have? Now, it's very easy to understand the curvature of a single wave function like a guitar string, like the particle in a box. It goes up and down. It crosses zero a whole bunch of times. Okay? You can do the same thing on these by just drawing a line through here. So let's look at the x-axis. Draw a line. You see the wave function goes up and down, and then inside probably up and down again, and then up again and down. So that wave function has a lot of curvature to it. Going down the z-axis, you know, it's, again, that wave function goes down and up and down and up and down and up. I mean, it's curving. Every time it crosses a zero, that's a node. And so you could just walk a line through these orbitals and see how many times they change sign and rank them. That's how high in energy they are, the more times they change sign. And then this is the other one, the x squared minus y squared, aimed right at hydrogens that are out of phase. And so again, it squished that d orbital, made it into a smaller box, and you've got lots of nodes. So a higher energy. So that pushed those up into the antibonding region. Yes?
Why did D get squished and not the 1s at hydrogen?
I don't know, actually. This is the pictures that come out of Gaussian. I would have not squished it that much if I was just drawing these. What Gaussian is doing is it's putting electrons in these orbitals and minimizing the energy of that orbital. Even though it's an antibonding orbital, it's minimizing the energies of those orbitals. So it does what's called a self-consistent field. It adds these 1s orbitals in and d orbitals in at different strengths until it gets sort of a what we call a self-consistent field to solve that Schrodinger equation. And once it comes up with sort of the minimum energy for that particular orbital, then it stops and goes on to another one. And so that's, yeah. So I don't know why the relative sizes of those orbitals are what they are. And it's going to be somewhat dependent upon the calculation that you do. You know, is this the exact true shape of that orbital? The shape in general, yes. But in terms of how big the 1s's are versus the d's, that might change a little bit if I change some of the parameters of the calculation.
Does that mean that all the lower orbitals get shrunk at a relative? Okay, does the ratio of the
Yes, yeah. So it tries to keep, like it tries to use, you know, if it comes in with 3 atomic orbitals, it makes 3 molecular orbitals, and it's going to use, you know, some percentage of each of them, and those percentages should add up to 1. You know, so yeah, if it uses a huge amount of the 1s in the upper one, it's probably going to use less of it somewhere else. And you do kind of see the 1s region in the bottom left here is smaller than it appears. It's still pretty big, but it seems smaller here than it does there. So. And I was, you know, I was kind of debating when I was making these notes whether I should just draw it by hand up here or let Gaussian give us the pictures. And I decided to go with Gaussian because it's more and more used in research, and the more used to using it you are, the better you're going to be. So you're going to start to see, well, we do see it all the time in research presentations and posters. They'll show molecular orbitals. And so I want you to be very comfortable in seeing images that are generated by these electronic structure computations. So then we have the 4p orbitals, and the bonding arrangement, and then here's the 4p antibonding. So I like these. So here the 4p's are huge in the antibonding, and the 1s's are small, whereas in the d orbitals they were big. So again, it's kind of that conservation of how much of that orbital you use in mixing in these molecular orbitals. But do you see the nodes? Here, let's look at the z axis. This low energy one, just if we draw a line, you see it's, say, positive here, goes through 0 and negative there. And if we draw the line down the z-axis here, it's positive, negative, positive, negative. Did that help or hurt? Yes?
Did the intensity like when you're crossing the axis and you go out for positive, you walk along the line of the green, or is that not relative to the intensity of the peaks at all?
I'm not really trying to be that careful. I'm just saying, yeah, it's positive and negative where the changes color. Yeah. You can actually get the amount of electron density in that orbital by Gaussian will tell you that. It'll sort of tell you what percentage of the electron is in that volume of space. And these volumes are generated to where they are, I think at like 96% of the wave function is captured by these shapes. Okay, or it might be 90. It's like a 0.004, so that'd be 99.6. So not 96, but 99.6. The default is 0.004 ISO value. What they mean ISO value is sort of, if you walked along that orbital, the electron density would be 0.004 everywhere you go. Okay, and so everything inside that orbital will be higher. And so then there's the 4s. Again, the bonding arrangement, it's in phase with all of the hydrogens. And here's the antibonding 4s. So we have what was a spherical 4s. Now it's pinched into a kind of a square. It's hard to see with this projector. My screen looks a little better, but you can see it looks like one of those dice that have sort of soft edges on it. So it's being squished by the presence of those orbitals around it. And so that's antibonding because there's nodes that break the bonds. So between the chromium and the hydrogen, there's a node here and a node here, etc. And now you can kind of see when I said we put hydrogens on the faces of a cube, that's an octahedral arrangement. So let's get into the selection rules. This is the part where I will require you guys to do these kinds of things. This is appropriate for the homework, etc. So we have this HOMO LUMO gap. So the question is, can we do a D to D transition or do the HOMO to LUMO? Let's look at the D to D first. So can we go from this D orbital that's occupied to the D orbitals that are unoccupied? We can look at the symmetries that are involved. And so this is the transition moment integral. First of all, could you have come up with this transition moment integral? You look down here at this energy level diagram and you see that the symmetry of these here are EG. And so this doubly degenerate row goes here, that's EG. And these are T2G, so those go here. What goes in the middle? Light. And so you go find that character table, the octahedral character table, find X, comma, Y, comma, Z, that's light. X polarized, Y polarized, Z polarized. And you come across the row, that's T1U. And so light goes in the middle. Now this is pretty ugly for the direct product table because we have lots of, the E's are doubly degenerate and the T's are triply degenerate. So we have lots of multiplication sets. So we do the T1U times EG, and we get T1U plus T2U. And so then we just multiply these through that set. The T2G is multiplied by the T1U and multiplied by the T2U. So we get this full set of results. And you're looking at this full set of results, and you're looking for top row. We have an A1 here, but it's a U. And so it's not allowed. Yes?
Couldn't you have just done that from the G's and U's?
Yeah. Exactly. So you look at the G's and U's and you're like, well, I know that one U is going to poison the stew. Okay. And so we've got a couple of G's and then we've got that one TU in there and it's going to be a mess. And so it's not going to be allowed just from GU symmetry. Okay. But we have strongly colored substances that are octahedral. So we'll talk about that in a second. Now what about the HOMO to LUMO transition? So we have those 4p orbitals, And could they go to the d, x, z, x, y, and z, y orbitals? So here's our transition moment integral. The p orbitals are T1u, light's T1u, and the d orbitals are T2g. I had to color code this one because this is a big mess. All right, we've got a huge set of results from the first multiplication. T1u times T1u gives A1g plus EG plus T1g plus T2g. And so this one I color coded T2g times the A1g gives T2g. Then times the EG gives the dark blue set, okay, the next two terms. And then times the light blue, T1g gives the light blue set. So there's 4 terms to that one. And then the black to black gives the black set at the bottom, okay? So even though it's tedious, it's not hard. And that's one thing you're going to learn from this class. Some things are not hard, but they're tedious. You're like, oh, great, I got it. I'm going to have 12 terms here, or 13 terms. I got to work my way through. That's okay. You know what to do. Just do them one at a time. Hack your way through it. And eventually you see, hey, I found an A1G. It contains an A1G term. Therefore, it is allowed. Okay, so the HOMO to LUMO is allowed in this substance. Okay. And so this is the coordination chemistry happening in aqueous solutions. We have waters popping on here instead of hydrogens. We have the same kind of thing happening with these orbitals. Okay. Now, this is the tetrahedral set. We've got 1 minute. There's no way. Okay. But I want you to walk through the tetrahedral set on your own, and there's also a video on it that is on YouTube from last year. But let me go to the end and skip past these. Look at those weird looking orbitals. Okay, yeah, tetrahedral molecules are strange. Same kind of symmetry rules that we've got, same color coding things. And so here we've got the HOMO to LUMO is allowed, and then we've got the D to D transitions. Okay, they're allowed. And that's where we have these beautiful colors for the aqueous ions of the transition metals. Different pHs, different kinds of things you can put around them. You can put water around them. You can put ammonia in there, and ammonia will snap on there. It's a little stronger than water. You can put thiocyanate or cyanide ion or even carbon monoxide, and you put different ligands. They're not covalently bonded to the chromium. They're just associated with the chromium in aqueous solution, and these are all the colors that you get out. And what's given us these colors is playing with that HOMO-LUMO gap. You put a different ligand in there, you change that box length just a tiny little bit, and you get a shift in the spectrum, and you get a different color. This was discovered early on that these metal-rich ores were good for dyes. And so the very first pigments in paints and so on had inorganic pigments. They didn't have polymer pigments. They didn't have molecules like these organic dyes and so on. And so that's a great way to tell if your painting is a fraud or not, some of these ancient paintings, whether they have an inorganic pigment or they're using some dye that was discovered in 1970. And so that's kind of a neat little trivia to end on. So it's all about the molecular orbitals.